Hello, guys. So welcome again. This is a continuation of our lecture on modeling with first-order differential equations. So in this lecture, I want to look at Newton's law of cooling and how you can use it to model the temperature changes of a body. Okay. So Newton's law of cooling is one of the models can actually use to describe the rate at which the temperature of a body or a room often is used as well is changing with time. Okay, the rate at which the temperature is changing. Now, if T here is the temperature of the body at time T, and Ts is used to represent the temperature of the surrounding or the environment or the ambient. Okay. Then the law says that the rate of change of temperature is proportional to the difference between the temperature of the body and that of the surrounding. Okay, so rate of change of temperature with time is proportional to the difference between the temperatures, that's the body, and then the surrounding. And K here is just the constant of proportionality. Okay, so it's simple. In this case, it's simple. Well, it can become complicated depending on what you want to add, but we just want to look at this simple case. Now, if the body is cooling, then of course the temperature of the body is greater than the temperature of the surrounding, so it's losing temperature. And so if it's cooling, we expect the change in temperature with time to be decreasing, right? If you like, to be negative, because this is cooling. Now, but if it's cooling, then T has to be greater than this. So this guy is positive. So for this to be negative, we expect K to be negative. In the same way, if the body's temperature is increasing, then we expect this to be positive, right? The rate of change of temperature has to be positive. But if it is, if it's increasing, then of course the surrounding temperature is greater than the temperature of the body, or the temperature of the body, like, is less than that of the surrounding. So T minus Ts is negative. For this to be positive, K has to be negative. So in either case, we see that K has to be negative. Okay, so this is a negative constant. Okay, so this is a simple first order differential equation, actually separable, so it's easy to solve it, right? We can easily separate variable and solve. So separate variable, solve for T, is just ln of T minus S is equal to KT, and then you simplify it. And you get T is equal to Ts plus C e to the KT, where C is just a constant, a positive constant. Okay. So basically, this is the solution to the model. Good. So to apply it, in other words, to find the temperature at each time T, you need to often you are given the temperature of the surrounding, and then you need to find what C is using the initial condition, and then you need to find what K is. Well, to get K, often you are given two conditions. You are given that the temperature at a certain time is given by something, and you can often use that. Apart from the initial condition, you can often use that to find what K is. Once you know K, you know C, well, you can apply the model to the problem. So let's look at an example. You have a hot cup of cocoa drink, has a temperature of 100 degrees Celsius, so it's very hot. Within 5 minutes, the drink cools to a temperature of 70 degrees, all right? So in 5 minutes, it cools from 100 to 70. You want to determine how long it will take for the drink to cool to a nice temperature of, let's say, 45 degrees Celsius in a room temperature of 25 degrees, okay? So in 5 minutes to 70 degrees, that is still hot for you. You don't want to drink it. You want to wait and see when it will be nice enough, let's say 45 degrees, then you can start drinking it. How long will it take? Well, you can use Newton's law of cooling to determine that. Okay, so how do you do that? Well, the temperature of the surrounding will be the temperature of the room. So we'll take the room temperature to be the temperature of the surrounding. So Ts will just be 25 degrees. That's the temperature of the surrounding. Now, the initial temperature is 100 degrees. So we'll say T at 0 is 100 degrees. Okay, so if you plug this, if you use this and use that, you get your model, right? from Newton's law of cooling that the dt, well, change in temperature with respect to time will be K of T minus S. Well, you can substitute 25 here if you want to. Then T at 0 is 100 degrees. So you have an IVP, first order, okay, that you can solve. Well, we know the solution. T will be Ts, which is 25 plus C e to the KT. To find C, we use the initial condition when T is 0, when time is 0, the temperature is 100, which means C plus 25 will be 100, which means C is just 75. All right, so you plug 75 back here and get T is equal to 25 plus 75 e to the KT. Well, as it stands, you still can't apply it because you don't know what K is. So you also need to determine what K is. Now in the problem, we are also told that in 5 minutes time, when T is 5 minutes, the temperature has cooled to 70 degrees. So we can use this and that to help us find what K is. So when T is 5, T is 75. Temperature is 70 degrees, sorry. And so use that. So when temperature is 70, this is 25, we know that 75 e to the time is 5 minutes. So put 5 here times K. Then just solve for K here. If you solve for K, well, this is just algebra, it's easy. Solve for K, K is negative 0.1022. And then you can plug it back into this, and that gives you the expression for the temperature. So now you can use this. Okay, so you have a nice, simple equation that you can use to predict the temperature at each time T. Okay, good. So now the question says that how long will it take for this guy here, this temperature to become 45 degrees before you start sipping? Okay, so so you need to find what T is, small t here. So plug in 45 degrees into here and solve for T. That's basically it. So put T 45 degrees in the left-hand side of the equation, and you get this expression here. 45 is 25 plus 75 e to this. Take this, that's give you 20, divide through by 75, you have this. Ln of that is negative 1.3218. Divide through by this guy and get T is 12.9. So about 13 minutes. So if you want it to cool to 45 degrees, you have to wait for about 30 minutes, and then it will be nice for you to start drinking it. Okay, so that is just an application of Newton's law of cooling that you can use. You can also use it to determine, you know, not just drinks, the temperature of a room, temperature of a building, and all kinds of stuff. Even in criminology, I will show you one here that you need to actually solve. Okay, so let's look at let's analyze, do a few analysis here. Okay, this is just extra. This is not part of the question. So if you plot the expression, this temperature as a function of time, this is what you're going to get. Initially, when T is 0, temperature is 100, and then it begins to decrease, right? The temperature begins to cool. In about 30 minutes, you are right there, about 45 degrees. So at this point, maybe that's when you can start drinking it if you want it to be at 45 degrees. All right. But then, of course, you are in a room of a temperature 25 degrees, so it will still continue to cool, right? Cool. Until here, this shows that after a long time, as T goes to infinity, it cools and approaches the room temperature of 25 degrees Celsius. Okay, you can actually find it from the expression. You can find a limit as T goes to infinity here. Find a limit as T goes to infinity. This guy goes to 0, and so T becomes 25. So as T goes to infinity, your temperature cools to the room temperature, which makes sense, right? You are in a room of temperature 25. You have something that is hot. Okay, of course, because it's hot, hotter than the ambient, than the environment, to begin to begin to release heat, right? And so the temperature will cool, but it cannot cool below the room temperature. It can't cool below the environment. So after a long time, it will cool to a temperature which is equal to the room temperature. So that makes sense. Okay, so that is what this is telling us. Good. This is what I just said. You can find a limiting value. That is the limit as T goes to infinity of temperature is 25 degrees. Okay. Now, the model is actually not able to tell us exactly when the temperature will reach the room temperature. Okay. And if you go back, this is because if I want to know when the temperature will reach room temperature, I have to put here to be 25 and solve for T. But if you do that, you are not able to do that, solve it. If you put 25 here, 25, 25, they cancel out, you get 0. Divide through by 75. So you have e to the negative, this expression is equal to 0, which is of course unacceptable, right? That is because this guy, that the exponential expression does not go to 0. All right, so you can't put 25 here and solve for T. But what you can do actually, that is you can plot as we did here and see, give and get an estimate, right? An approximate time when the temperature of the drink will reach the room temperature. And that is, if you look at this cools, right? Then beginning to approach the room temperature. So about, let's say 15 minutes time, okay? Or if you like 60, I'll go for 50. In about 15 minutes time, then the temperature of the drink will be about the room temperature. So you can use a graph to help you estimate the temperature it takes to reach the room temperature. But you can't use the model, the expression, the equation we have there because of what I just said. And so that is what I explained here, okay? You can plug this into the left-hand side. So, but you can use a plot, right? You can do as we did there, just a plot of it, and that will help you to estimate it, okay? Good. So once again, as I mentioned, this is these problems are practical, all right? So this is a question that you should try. Okay, so this says that at 9 a.m. on Easter Monday, the temperature in Kaswa, that is a suburb in Accra, or a suburb of Accra, was 25 degrees Celsius. Okay, now Inspector Awuni arrived at a crime scene to meet Corporal Mauto, looking at the lifeless body of Miss Anita. She's been murdered, all right, beaten to death by an armed robber. Okay, now the experienced inspector said there were several suspects, but if they knew the exact time of death, then the list of suspects could be narrowed down. All right, Corporal Mauto then brought out his thermometer and measured the temperature of the body. It was 35 degrees. So the temperature of the dead body was 35 degrees Celsius. He then left to a chop bar for breakfast. He returned at 10 a.m. That is 1 hour later. Remember, at the time was 9. So he returned at 9 a.m. to find the body temperature to be 33.5 degrees. So the body temperature is reducing from 35 to 33.5. Question is, what time did the murder happen? Okay, so according to the inspector, if they could determine the time the murder happened, right, then you could trace back and say, okay, around that time, we know of some criminals around this area. Around that time, some of them passed here, or a couple of them passed here. And so it helps you to narrow down the list of suspects. So, but this hint is important. You have to assume that a normal body temperature is 37 degrees. Okay, so assume this and try to find what time the murder actually happened using Newton's law of cooling. Okay, good. So I'll end this third example on the modeling with first order differential equations. And then when we come back, we'll end with the logistic model or the population models. All right. So that will be it for this one.